When I was young, I was fascinated by elevators. When you went up, everything else seemed to go down. When you go down, the world goes up. When I got older, I got used to the notion that the world isn't really going up or down, but that the only one that was moving was me. Yet, it is somewhat a mistake to ignore what we see. The truth is that going forward, for example in a train, does not affect the Earth too much. But the Earth is moving relative to the people inside. That's the basis of relativity. Sound simple? Someone moving at relative speed to someone else would look to the other one as if he was moving in opposite direction and in the same speed, and that is as complicated as it gets. But something did not fit. You see, the knowledge gained during the last decades of the 19th century gave more than a hint to the possibility that light does not adhere to relativity. Everyone, moving fast or slow, seemed to be having essentially the same speed of light. It seems benign, but look at that. This craft travels at speeds close to the speed of light. What you just saw was two simultaneous lightning strikes at the forefront and back of the craft. Now, you can see the light from both events coming towards the person in the middle as he is moving towards the light from the front, and the light from the back have to chase him. So, he will see the lightning from the front first. So far so good. However, and pay close attention to this, relative to him, the light comes at the same speed and takes the same time to reach him from both directions. So for him, seeing the front lightning strikes before the one in the back means the front striked first. Something is very wrong. Or is it? The greatness of Einstein was that he managed to understand it is possible to reconcile relativity with a notion of unchanging speed of light. He did that by adding something to the theory of relativity. Time. Time, he said, is relative. Simultaneity is relative. And that's not all. Let's take a look at the length of the craft. We'll assume we can estimate the distance between the lightnings in the photo. As we've seen earlier, relative to the person inside and the craft, the front meets point A first and the rear meets B a little later. So from inside, length A to B seems to be shorter. This is what's called length contraction. The factor by which the contraction occurs is called the Lorentz factor. The Lorentz factor stays close to 1 for most velocities, but rises fast when approaching the speed of light. In almost the same way, it can be shown that a moving clock will tick slower than a stationary one, and by the same factor. The general rules of relativistic location and time have been summarized by equations called the Lorentz equations. These equations have some other interesting implications. For example, if someone throws a ball in a moving car, it's reasonable to assume that we can sum that speed and the speed of the car, and that will be the speed of the ball relative to the outside world. The Lorentz equations tell us it will actually be slower, never over the speed of light in vacuum, by the way. But the most famous implication stems from the derived equation for energy. What we get is energy equal to the Lorentz factor multiplied by mass and the speed of light squared. While fast things have a lot of energy, when they are standing still, Lorentz factor of 1, they do have some energy, quite a lot actually. It seems that everything has energy just by having mass. Releasing or capturing energy, by the way, changes the mass. While these predictions of his theory seem weird at best, and are definitely not apparent on our day-to-day experiences, they have been tested innumerable number of times. Clocks really do tick slower at different speeds, lengths do change, and so on. Time is relative, and everything that stems from it is, well, weird, but real.